Okay, good. So, let's start. So, good morning, everyone. Welcome to Kaneka's summer school in number theory. My name is Liang, Xiao. I'll be giving a series of lectures on algebraic number theory. Just kind of if you've learned it before, it will be kind of a review of what we have learned. If you haven't seen it before, well, you can, I guess I'll help to give you some sort of a sketch of what's going to happen. So the idea is how to summarize probably a semester-long course into sort of 4-hour-long course. We'll see how that goes. Well, if you have any question anytime, just raise your hand, or just say it out. I won't be able to kind of see you very well. So yeah, and feel free to ask me questions. So the first lecture, we're gonna just somehow talk about very basic number fields. By number fields, I mean a finite extension of the rational field. So before anything, let me sort of explain why I want to look at number fields. Why do we care? I mean, for a lot of people, somehow at the end of the day, we care about rational numbers, integers. So here, I'll give you one reason. Well, I have many reasons, but here's maybe one reason. I guess I'll explain it come from an early proof. Well, proof, not quite a proof, of Fermat's last theorem. So what that is you want to show that you have this Fermat's equation, x to the p, y plus y to the p equals z to the p, where p is alt prime. You want to show no non-trivial integer solutions. So that was Fermat's last theorem. And of course, this was proven by a very extremely difficult method, or a very highly technical method. But there's something that was known like over 100 years ago. You can do the following. You have z to the p. Let's write this, because p is odd number, so you can write x to the p plus y to the p as x minus negative y to the p. And then, just like you factor x squared minus y squared, you have x to the p minus something to the p's power. You can write it as x minus negative y times x minus p sort of unity minus y, and so on, to x minus zeta p to the p minus 1, where zeta p is e to the 2 pi I over p. Just like you factor x squared minus y squared, you have x plus y, x minus y, you have this factorization. And let's rewrite this, well, I guess it's traditionally, people like to write it as this. Okay? So now, we want to solve this equation with x, y, z in the integers. So here's some sort of relatively, let's make some sort of naive observation to see why this helps. So suppose, which is a big if actually, that if you adjoint p derivative to the integers, and this will give you a ring. If this is a principal ideal domain, PID, then we can assume, well, first of all, I can assume that x and y are co-prime, because there's no reason to keep a common prime factor. And after that, you see that this x plus y and this x plus zeta py, they're very close. If you take the difference, it's like zeta p minus 1 times y. Because x and y are co-prime, you'd expect that this x plus p and x plus zeta py are, let me say, almost co-prime. They're not, well, you can't quite conclude they're co-prime right away, because there might be a small factor of like zeta p minus 1. But except that factor, it's almost they're almost co-prime. And therefore you have a, p factors of things which are co-prime to each other, and hence are sometimes almost p power. P's power or something. So that's something somewhat very rare to happen. Like if you have two numbers, right? Their sum is a p's power, and then the x plus zeta py is also a p's power. That rarely happens. And so that you can explore that fact to show that there's no solution to this. So of course there's a lot of work to be done after that. But then of course this gives you a way to approach the problem. So the upshot I want to say, maybe I should say this. So Kummer, using this kind of method, Kummer, that's centuries ago, shows that this proof works. Not only this z adjoint zeta is PID, but also when this ring is, let me say, almost a PID. I'll come back to this later to talk about what really condition is. So that's I guess triggered the study of the algebraic number theory and algebraic number field. And I want to say that also one major remark that Kummer used this method to prove this for all odd prime p less than 100 except for 3 primes. So he proved a lot of this Fermat's theorem actually. So here's the upshot. I want to conclude at the end of this example, which is that studying bigger field help understand this Delphin-Time equation. Over either z or q. Okay? So even if the original equation like this one, x to p plus y to p equals z to p, is written, you're asking about asking about integer solutions or rational solutions. But the solution sometimes involves understanding this in a bigger field. And it really helps if you go to a bigger field. So that's what we want to talk about number fields. So let's get down to study number fields. This is by definition just a finite extension of Q, the reference. So usually people write this as F over Q. That's a standard way of writing this. There's a primitive element theorem that if you have a finite extension of a field of characteristic 0, it's always generated by one element. So this where alpha is a 0 of an irreducible binomial. Let me call it hx in Q adjoint x. So the degree of hx is the same as the dimension of this f as a Q vector space. Sometimes we write this as f colon Q. We're gonna use n to denote that degree of the extension. And I have this alpha to be the 0 of these irreducible polynomials. Let me write other zeros as, or all the zeros maybe. Maybe I include alpha here to be alpha 1 through alpha n. Okay? So now we're going to think of this. So the idea is I don't want to think of alpha as an actual complex number. In some sense, I want to think of alpha as just the 0 of this polynomial. In some sense, I want to think of my f, instead of as sort of adjoining some concrete number alpha, I want to just join a abstract variable x, except that I set h of x to be 0. So this is some sort of abstract number field. But whenever we want to talk about, want to relate to the reals of the complex, we talk about something called embeddings. So when we choose a way to embed this into C, where I'm allowed to send this x to, somehow in our mind, I can send it to the alpha 0. So this is called, let me call it tau 1. I can also send it to other zeros of the same polynomial. So these alpha 1 and all the alpha i's. So they all form different embeddings of f in C. And there are precisely n such embeddings. Let me give an example. So let's say f, I want to take it to be q adjoint cube root of 2. Okay? And so this, of course, this is a 0. I don't know. I mean, this is a 0, x cubed minus 2 equals 0, of course. Let me write real embedding. I'll explain what that means. Real meaning it's going to embed into the real number. So I'm going to write tau 1 of f into C, but somehow the image will land in the reals. The way you want to send this is that I want to think of this again as qx over x cubed minus 2. You want to send the x to the actual cube root of 2. Right? You see that if you send x to cube root of 2, then the equality here, x cubed minus 2, will be automatically 0. So therefore, you have a map from this quotient to R. That makes sense. Similarly, you have other embeddings. There are complex embeddings. Let me write tau 2. Okay, tau 2, tau 3, that's fine. Go from F to C. And you can think of this as Q, right, X over, and then you want to send X to tau 1, we'll send it to cube root of 2 times the third root of unity. You see, X cube root of 2 has 3 roots. Cube root of 2 and cube root of 2 times third root of unity, and then the other one. So in other words, what I'm implicitly saying here is that if you join cube root of 2, and that's just the same as q adjoint this times this, or that's also the same as q adjoint the other roots. They're just different. They're somehow abstractly the same thing, but somehow you're choosing different embeddings of realizing the field as a subfield of C. Right? And also I want to point out that because this zeta 3 is minus 1 plus root of negative 3 over 2. And zeta 3 squared is exactly complex conjugate of that. So these two are complex conjugate of each other. So I want to point out this is some sort of reflection of a general fact that given an arbitrary number field, you have some number of real embeddings, and you have some complex embeddings. But the complex embeddings always come in pairs. Make sure to say that complex embeddings always come in pairs. Because when you have a complex embedding, you can further apply a complex conjugation, you have a different embedding. Okay? But altogether, there are altogether n embeddings if the degree of f over q is n. Are there any questions? So, I'll talk about a very technical thing. So I want to, for alpha in F, I want to define its choice to be, I'm going to write this choice of f over q of alpha to be the sum of all the embeddings. And it's not trivial fact that if you sum all the embeddings of an element, you actually get back to in Q. So I have some exercise here. Oh, I should tell you this. So I have some exercise printed out here. You can also find it online if you want to get it later. In that exercise, I will tell you how to prove that the traces are actually in Q. Similarly, I can define norm to be this. But instead of taking the sum, you take the product. Once again, this will leave it in Q. Okay? So now this is all about the field. If you recall earlier, let me turn back this page a little bit. So when we talk about this application of left field, I'm really interested in this Z adjoint theta P. It's not a field. This is somehow the ring associated to that. So this is something we call the ring of integers. So basically the idea is that now I have my field f equals q joint alpha as an extension of q. Okay? We know that inside the q are the integers. That's something we work with. And now we want to understand how to define that thing here, which is sort of ring of integers for number field. Okay? That's something we want to explain right now. So let me so here's maybe a naive guess. So you can start with an alpha. There's obvious, I can just maybe look at from my last term example, right? I start with a sort of adjoining some zeta p, right? So you can do this. Maybe I can just take OF equals Z adjoint alpha. Well, there's a bit of a problem with this. What's the problem? Well, you can say, okay, note that Q alpha is the same as Q2 alpha. You can either join alpha or 2 alpha to the same field, and you're gonna get the same, like I join them to Q, then you're gonna get the same field. But of course, definitely Z alpha is gonna be different from Z2 alpha. In some sense, the ring of integer would depend. If you were to define it this way, it would depend on the choice of the generator alpha. That's not very ideal. You can also argue maybe there's some obvious way to kill some sort of denominator, some sort of coefficient too. But later on, we're going to see some examples where these alphas, you can choose other things which doesn't quite look like 2 alpha. For example, you can choose most of the time you can choose, for example, for many cases, for example, you can choose x alpha squared plus 1. It might be the same field, maybe. But then it's hard to tell whether alpha is better or alpha squared plus 1 is better somehow. So this is not a good way. That's what I say. There's no good way of choice of alpha. But instead, we're going to do the following. We're going to define in some sort of abstract way. So I want to define it to be, this is a ring of integer. F. So this will be all the elements beta in F, such that the minimum polynomial, let me write it down, minimal monic polynomial of beta in Qx as coefficient in Z. So by an element beta in F, with a certain element, you can always find a polynomial of minimal degree, such that F beta is 0 of that polynomial. And you can always normalize the polynomial so that the leading coefficient is 1. I want to do that so that at the end of the day, all the coefficients, like if beta is in the ring of integers, then the middle polynomial of that has coefficient Z. It turns out this is the same, not very easy to show, but it turns out that's the same as saying that beta is a zero of a monic polynomial in Zx. Namely, this polynomial does not have to be reducible. You prove this by, I guess, factoring the polynomial in Zx, and you show that the factor that beta is zero of is actually also have coefficients in Z. That boils down to Zx as a unique parasitic domain. Okay, so here's maybe some example. It's rather abstract. I guess it's better to give an example. So the, I guess, very first example many people use when talking about number fields is the quadratic fields. Q joint root of D. For D a square-free integer. Maybe I should D not equal to 1. Square-free means that when you factor the integer D into a product of primes, there's no p squared in the factors. I mean, otherwise you can just take it out from the anyways. So then, the ring of integers in this case is, for most of the cases, it's Z a joint root of D, where D is common to 2 or 3 mod 4. The other case, when D is common to 1 mod 4, you have something doesn't quite look like integral. 1 plus root of D over 2. That turns out to be in the range of integers. Here I didn't have the case where D is divided by 3, because if you divide by 3, then it won't be square free. You can take out the factor 4 from the square root. Okay? So let me explain this a little bit, where this comes from. So I want to show that this is actually a zero of a monic polynomial with coefficient Z. So why is that? Well, let's try to build one. So I can do this. Right? But this is not, of course, this is not the coefficient not in Z. What I want to do is I want to multiply, excuse me, this is negative. Multiply is some sort of conjugate. If this is negative, this is just really a complex conjugation. But if this is positive, it still makes sense to talk about the kind of a conjugation in some sense, in the real quadratic field. You just turn the root of D into negative root of D. Okay? Now let's multiply these two out. So what do I get? I get x squared. I'm just going to concise calculation. So you have, then I'm going to subtract this, this 1 plus root of D over 2 and 1 minus root of D. Sum them. So I end up getting negative 1, negative x for next term. And for the last term, it's going to be plus, 4 and 1 minus D. 4 in the denominator and 1 minus in the numerator. Think a little bit. Now you see that if D is congruent to 1 mod 4, this last term is actually in Z. So therefore, although this 1 plus root of D over 2 doesn't look like very integral, but it is a zero of an integral coefficient polynomial. Okay? Good? So this is one of the examples, honestly. Oh, you know what? Let me stick here. Before moving to the next page. So just for a concrete example, if you do Q or joint root of 3, let me just write it. Q joint root of 3, that's just Z a joint root of 3. However, if you do Q adjoint negative root of 3, no, that negative 3 is common to 1 mod 4. So you have Z adjoint that. Alright? These are somehow further examples of this example. Let's see, more examples. If I take F to be Q adjoint theta N, theta N is the answer of the unit. Okay? In this case, OF is actually just Z adjoint zeta. You know, also this is called the cyclotomic field, I should say. If your joint ends with infinity. Then it looks like all the examples we saw. I mean, like in the quadratic case, of course, that's what the ring of energy looks like first. And then this cyclotomic field is always, there's always kind of a generator here. Then I'm going to ask a question. Is it always true that my OF is always Z adjoint alpha for some alpha? Let's maybe look at another example. Let's see. Let's start talking about cubic fields. Degree 3. Adjoint cube root of 10. This is my F. It turns out, if you run and write, let's see. Okay. It turns out that OF is a little bit bigger than the adjoint cube root of 10. You have to adjoin something like this. They're kind of a sharp. You can see that. It's not that in some sense. And these two kind of share some similarity if you think about it. So this is like 1 plus alpha. This is like 1 plus alpha squared. Here's over 2, here's over 3. And you can find such examples somehow a lot of time. But it turns out this is not quite a counterexample. But it's an interesting example in the sense that turns out that the later guy looks like 1 plus alpha squared over 3. This can generate cube root of 10 somehow. You can recover cube root of 10 by some algebraic expression of this thing. So this seems to be also supporting the case that, first of all, I want to say that even in some cases OF equals Z alpha, the alpha might not be something you would think. But secondly, actually, this is not, so this is not always the case. So here's an example. So first the counterexample. Starts in cubic. All the quadratic field, of course, they're generated by one element. So hopefully I got it right. Oh shoot. Square minus 2 alpha. I think this is minus 8. So play with the coefficient. One of them is, I think this is, so you can check this is irreducible, unless I get a signs wrong. And as it turns out that this one, there's no, so let me call it, is not of the form, excuse me, Z beta. For some beta in this way. In the exercise, maybe for the next lecture or the after, I'll give you a way. Somehow I'll explain away why this is not generated by one element. Okay, so that's not quite true. But what are true is that there's a basic fact of OF. OF is a free Z module of rank equals to n, which is the degree of the extension. By that, I mean that you can find alpha 1 to alpha n in the range of integers such that, I guess maybe I'll just try it this way. So OF is equal to A1 alpha 1 plus
A and R prime, where A1 and ANs are NZ.
All right. And also, there's another fact that if beta is in the range of integers, earlier on we said that the choice of the norm of an element in the member field belongs to Q. Now, if beta is in the range of integers, then the choice of beta is in Z, and the norm of beta is also in Z. Okay. So, are there any questions before I move on to the next one? We talk about how to visualize these OFs. So, how to visualize OF and compute OF. In some cases, not all the cases. I just give you some sense of how this kind of works. So let me start with talk about this by an example. So I'm going to use f equals q joined root of 5. We talked about earlier, there for every number field, there are same number of embeddings as the degree of the extension. So I have two embeddings, tau 1 and tau 2. You can embed q to 2, 5. You know what? Let me I'm going to send the explicit a plus b to 5 goes to a plus b to 5 or a minus b to 5. Okay? Now, I really want to visualize it by drawing a picture of this. So we'll have two coordinates, right? So let's see where the So let's see where, if I take z, I join root of 5, I mean, using the same embedding into R cross R, I want to say this becomes a lattice. Let's see what it is. Let's see what I mean by this. Okay, what is z? I join root of 5. So let's see, I have 0 here. Let me use 0 here. Okay? The number 0, under the embedding, let's get into that got embedded into the point 0, 0, because 0 would go to 0, 0. So now where does the number 1 go? Well, we have a 1 here. It's going to go to 1 and 1, right? So I should put a 1 here. So this is the number 1 in z root of 5, but the actual coordinate in this under this embedding is 1 and 1. And same for 2. If you have 2 here, it's going to match 2 and 2. So my number 2 is placed here. 2 and so on. So you can imagine the negative ones here and all the way. And so on and so forth. So all the integers are kind of in the diagonal line. That's because if you embed the integers into the reals, the two embeddings are the same. Right? So let's look at the other extreme, like root of 5. We'll embed root of 5 to R cross R. You get root of 5 on the first coordinate. And the second coordinate, you have the negative sign here. Right, so you get negative root of 5. So you get root of 5 in this way and negative root of 5. So roughly here. This is where root of 5 is. The actual coordinate in two-dimensional space is root of 5, comma, negative root of 5. And to do 2 times root of 5, we're going to get try to be proportional. Okay, so where does 1 plus root of 5 go? Well, you can think of it as kind of a vector space, right? You have this vector 0 to 1, 0 to... Then you can kind of start to kind of link this together. That's where 1 plus root of 5 is. And the actual coordinate is just 1 plus root of 5, comma 1 minus root of 5. And then you see that if you embed this z adjoint root of 5 into the two-dimensional real space, you're gonna get some sort of lattice. I don't know how to draw this. Roughly get some sort of lattice here. Okay. Okay. You get some sort of lattice. And of course, for a lattice, you can ask, what's the area of each of the, it's called fundamental area. What's fundamental area? In this case, what is equal to? Well, I guess you can check. So this is like 1, 1. So this is like root of, so this is all 45 degrees up, right? This is 45 degree up, right down. So it's like a rectangular here in this particular case. So this side is root of 2, and this side is root of 5 times root of 2. So I get 2 root of 5. Okay. Let's compute it. Like this is like root of 2, of course, and this is like this coordinates is root of 5. But I wanna, for what I'm gonna do later, I wanna do calculus area squared for some reason. So this is 20. Okay. Now I want to remind you that for Q adjoint root of 5, Z adjoint root of 5 is not a ring of integers. Just remember that over here, if D is common to 1 mod 4, the ring of integers, you have this 1 plus root of D over 2. So what I should have been doing is like looking at this one. Okay? So of course this Z adjoint root of 5 is contained in here. So all the green points are already in this, already drawn here. But we have just one, some additional points. For example, 1 plus root of 5 over 2. So that's precisely in the center of this. And also here, like you can add 1, so it means add 1 here. So this is plus 1, so 3 plus 2, 5. It's going to be a finer lattice than this Z adjoint root of 5. You should add more points. Basically, in the center of each of the box here, you put right in the center, you put a point there. It's going to be a finer lattice. And I can also ask the fundamental area of this finer lattice, which is going to be this one. Or you could draw a different one, but they'll give you the same answer anyway. So this fundamental area, well, you can somehow parallel move it. It's like half the area of the red region is half of the area of the green region. But if you square it, of course, it's going to be 1/4 of that. In this case, 5. Okay? So, this way, in some sense, we gave a way to actually kind of see what the range of integers are, see them using the embedding as some sort of lattice in this case, 2-dimensional space. But later on, we can kind of do something similar, like generalization. Is that when I have a number field, I want to consider all these embeddings. There's a small subtlety here that this f doesn't always go to R. In my case, it's like f embedded into the reals. In general, like it may not be real embedding. It's complex embedding. For the moment, let's forget about this here. Just pretend that these are all real embeddings. In the exercise, you're gonna work through something that somehow to solve this issue. This is all embeddings. And so supposedly this OF, the range of integers, is going to create a lattice inside this n-dimensional space. This sort of n-dimensional space. And I want to know the fundamental area of that in some sense, or fundamental volume of that. So I want to define something called a discriminant of just let me say here for alpha 1 for alpha n. You can define it over F. For all the elements in F, you can define the discriminant of them. This is defined to be the determinant. It's a little bit. I'll explain in a minute. Like that. It's kind of a big matrix. So why is this? Why do we define things like this? Well, I'm not sure if you learned this in linear algebra. Like if you want to compute the area or the volume of some sort of parallelogram or parallelepiped, one of the way you do that is like you do what I did here. But another way, for example, in this case, what you can do is that you can do the determinant of this coordinate, 1, 1, and then the determinant of the other coordinate, root of 5, negative root of 5. And then take absolute value. That's some sort of formula I'm not sure if you've seen before. This is some sort of general linear algebra. Like if you want to know the volume of parallelepiped, you take the determinant of the vertices. So this is the tau 1 through alpha 1 through tau n alpha 1. Those are the first column here. This is a point corresponding to vertex corresponding to alpha 1. And the next column here is going to be the vertex corresponding to the image of alpha 2, and so on. You take the determinant of the whole thing. Suppose you take absolute value of the fundamental area. So this is roughly somehow the fundamental area squared, because I put a square here. Well, it would be literally true if it's not complex embeddings, just real embeddings. Because of the complex embeddings, turns out this determinant actually could be a negative number. This is some sort of subtle things in the exercise that I kind of address. I won't have time to do this. But I think it's a good way to keep in mind that it's roughly the same as the fundamental area. Any question? I know this is somehow the difficult point of the first lecture. Okay, good. Very nice. So now, here's a fact. If alpha 1 through alpha n are actually in the ring of integers, then this discriminant defined is actually an integer. So definition, if I just give my alpha 1 through alpha n, just precisely the basis of the ring of integers, I can compute this discriminant. So if this is just precise, right? The alpha 1, the alpha n. So if these alpha 1 through alpha n are precisely the basis, namely, where is it? There. If this, we know that OF is a free Z module. Then I can find alpha 1 through alpha n such that OF looks like this. In a fancy way, this writes as Z alpha 1, Z alpha n. Okay, so these alpha 1 through alpha n are the Z basis of OF. Now, if I do have this, then we call. I'm going to write discriminant of OF, or sometimes still write discriminant of F. This is defined to be the discriminant of alpha 1 through alpha n as defined in the previous page. The discriminant. Okay. So this is I hope it gives you some sense of what this means. In terms of picture we had earlier, this means that you embed OF into this sort of n-dimensional space. It's the fundamental volume of that lattice. That's roughly what discriminant is. Just giving you some. This will be exercise later. If you have F equals to Q joint root of D, then the discriminant of OF or the F is either D
if D is common to 2 or 3 mod 4. It could be also 4D if D is, if D is common to 1 mod D, 4 is D. Otherwise, it's 4D. Sorry. Let me give an example. So here, Q attributed to 5. I compute the manual. This is really the OF here. Then the square of the fundamental area is 5, which is this 5 here. Root of 5. So that's somehow the first example we have here. Oh, sorry, I mean always D squared free. Whenever I read this, I mean D squared free. Okay? So why? So I want to say that, so next thing is I want to say how this discriminant, this construction can help us to determine what OF is. Here's maybe an example. Let me start with an example actually. So I start with F, not fact, this is an example. F adjoint Q alpha, where alpha specifies as alpha cube equals alpha plus 1. I want to show that OF is just Z alpha. Of course, I know. Of course, alpha satisfies this, integral coefficient polynomials. Therefore, it's in the range of integers. But then you have to show there's nothing else, right? So here's what you do. So you know that your Z alpha is going to generate a sublattice of OF. In the sense that you should kind of look at the picture here. Your OF is going to be the finer lattice here. Your Z alpha could potentially be the green one, but missing some points. Right? And now, if you look at the discriminant of the difference of the two. If you look at the discriminant of the larger lattice, versus the discriminant of the smaller lattice. If you see in this paper, in this calculation here, see, because the discriminant is really, you should think this is square root fundamental area. If the difference here, in this case, is 2, then the fundamental area square will off by a factor of 4. So in your case, Z alpha is going to be a sublattice of OF. So instead of the green one, the square of the green fundamental area should be the square of the red fundamental area times some sort of a difference, but squared, because our fundamental area is squared. Okay? And you can check that this is some sort of straightforward calculation, but I'm not going to perform this. You have the standard basis 1 alpha and alpha squared, and you just really compute the determinant of all the embeddings. 1, 1, 1, tau 1 alpha, tau 2 alpha, tau 3 alpha. There's a better way to do this. I don't have time to do it now, but I'm just saying. This is something you can compute. After a bunch of computation, you can show that this is actually negative 23. If I got it right myself. Okay? It's not that difficult. But now you're in this peculiar situation. The left side is negative twin solution prime. But we know that discriminant OF is an integer. And they're off by a square factor. But there's no square factor in this 23 here. So therefore this will force OF to equal to Z alpha. So force this factor to be 1. Because there's no square here. So that's how you use discriminant to help you to determine what OF is. In the sense that you first kind of approximate OF as best as possible. Like in this case, you would guess that somehow